Welcome back. It's the Mad Lad, and uh, now we're gonna keep moving along with the systems level design of the homing missile slash drone. Previously, we had a high level view of the plane systems. However, there's two areas where we can drill down further, and that's the flight controller and the single board computer. And we can kind of analyze, what needs to happen by looking at what other components, let's say the flight controller, is connected to, and that will tell us roughly what kind of systems need to be in place to make things happen. So I'm gonna copy the flight controller node and all the nodes it's connected to with a data link. That's the blue line. And I'm going to paste that on a separate slide. So this is flight controller systems. So, here systems is really the different bits of code, potentially, threads that we might have running on a microcontroller to make things happen here. And I'm gonna, oops, having some difficulties moving things around here, but I think I'm gonna move this aside, and I'm gonna make some nodes here. So I'm gonna copy this gray node. So we have, here are RC receiver nodes. So that means that we need to have a thread that monitors, the RC receiver. The flight controller that I'm going to be developing here, it's going to be based off of the Pt.2 microcontroller. And I know that in Pt.2 and Arduino, there is, well, let's take a step back, the radio receiver and transmitter pair is, I think, I have a FlySky transmitter and receiver, and that uses iBus. So we will have an iBus library that we'll have in our project, and we will have a loop to monitor our receiver. So let's call that RC receiver comms loop. So we're going to have some sort of a loop where we keep looking, where we look at the communication with the RC receiver going up. I'm going to kind of go in the counterclockwise order here. We have our single board computer here. So we have another communication loop here. So that's going to be the, the SBC comms loop. And we have an altimeter. So we're going to have another loop, which is going to be our altimeter. Let's call it altimeter polling loop. And let's do another one. So we'll have an IMU, or inertial measurement unit. In this case, we're going to be using the BNO55 microchip, or really it's a breakout board for the microchip. And then finally, since this is a flight controller, we're going to need to have a loop to handle the actual flight control. So we're going to have a PID loop, or really, the flight control loop. And part of that flight control loop is also going to be setting of the ESC and the servos. Well, the ESC and the servos are really the same kind of output here. That is, it's PWM kind of output. So I think these are going to be the main loops that we have at the flight controller level. The flight control loop will consist of some logic. So as I mentioned before, the flight control will have two modes of operation. One is, the guided mode, and the other mode is going to be manual mode or manual override. Because since this is a plane, once the guidance is over, you still need to be in control of it. So once you've tested your guidance system, you can then flip back into manual mode and use that to control the plane via the RC transmitter. So a flight control loop has the manual mode. In manual mode, what we do is we take the values that we got from the RC receiver and we just map those values to the output of the servos. In guided mode, the single board computer, the guidance system, it's going to be giving us a heading that we need to maintain to get to the target, and then we use a PID loop to get on that heading. And once you get the values from the PID loop, that's proportional integral derivative control loop, you take the values from there and you once again output them to the servos. IMU pulling loop, that's basically pulling that BNO 55 IMU AHRS. I don't remember off the top of my head. AHRS, attitude heading reference system, I think. So we pull the chip every, let's say, I think it's 10 milliseconds. I think it's a 100 hertz refresh rate on the chip. So you can pull it roughly every 10 milliseconds. Altimeter, I will probably be using an analog output altimeter, like a sonar sensor, and just pull it, every, let's say, the response rate of a sonar sensor is only so fast. So maybe we pull that every, let's say 50 milliseconds, so 20 times per second or something like that. We have and the altimeter, it's really an optional thing. I want to add it because I want to ultimately use this kind of system, this kind of flight controller to develop autonomous landing for winged fixed wing drones. So I would really like to have that in here. Plus, it's also nice to be able to just fly at constant altitude. Single board communications loop. As I mentioned before, the single board computer is responsible for providing the guidance information when we're flying in basically autopilot mode or guided mode. So it's going to be transmitting various heading data points to us. And in addition to that, we, meaning the flight controller, needs to be able to transmit the IMU information to the flight controller, to the single board computer, so that the logic on the computer in the guidance system knows what its current heading is. This way, when you're looking at when you're looking at the camera picture in your computer vision logic, you know how much your image is rotated uh, relative, to the world. Finally, we have the RC receiver comms loop, and there, let's say once every millisecond, we check our, I think it's UART, and check if we have any communication from the RC receiver coming in. So that sums up the high-level systems for the flight controller. And as I said before, we also want to take a look at what kind of systems, what kind of logic do we need to have at the single board, on the single board computer. So I'm going to copy this and all the nodes that are connected to it. Copy that out, create a new slide. So that's going to be the SBC systems. And over here, I'm going to paste in the diagram, the high-level nodes. Oops, move them over. So obviously, we're going to need to have the communications or the polling loops here. So this is going to be flight controller comms loop. And here we're going to be polling our flight controller, checking if it has any messages for us, or if we have any messages that we want to send it. Then we will have a camera, let's see what I call it here, polling loop. Okay. So we have camera polling loop. And let's see what else. So we know from this diagram that we also have a user interface web browser kind of thing. So we're going to need another piece of logic here to handle web hosting / UI. What else? Since the whole purpose of the single board computer is to provide guidance information, we're going to need to have, let's see, one thing we're going to need to have is a computer vision node. So my plan for this SBC or single board computer system is to have a ROS 2 or Robot Operating System 2 powered arrangement. So everything here is actually going to be a node in that system. So there's going to be a node which is responsible for the communications with the flight controller. There's going to be a node which will monitor or pull the camera. There will be a node which will handle the web hosting UI component. There's going to be a node which will be responsible for basically tracking a target on the screen, on the image that we receive from the camera. And finally, we're going to have a node which is going to be responsible for guidance calculation. So at a high level, that's what we have. So I think that's good for now. I have been working a little bit both on flight controller and the single board computer, and I have been playing around a little bit uh, with the airframes that I can put this on. Not enough to show yet uh, for the airframes. It's mostly, me trying things and failing. Like first time around, I got a tiny little foam airplane that's a little bit out of reach right now to show, and it was just too heavy. Once you put all the electronics on it, it can fly, but it needs to move super fast. And I don't expect the guidance system on a small single board computer to be very fast. So I want a plane that flies slow. So then I got a much larger airframe, and let's see if you can see it from here. Nope. The the background, yeah, you can't see it. Anyway, there's gonna be a picture, or I'm gonna have one stream where that's gonna be focused on the airframe, so you'll see it there. But it's a pretty big air. Well, not pretty big. It's pretty big compared to the first airframe. It's maybe a meter across or 3 feet across, or in wingspan. So, but it was still, I think, a little too small of a lifting area to have slow enough flight for what I wanted to do. So now I'm playing around with foam board airframes so that I can have a large airframe with a lot of lifting area that's fairly light. And if I crash it, who cares? It's Dollar Tree foam board. Just go and get a few more sheets and repair it. And generally, you can repair foam board stuff pretty easily, sometimes with just a little bit of hot glue. So, I've been working on that. I've been working on the flight controller. I've been kind of prototyping the different uh, loops or threads that we have in here. First thing, you try your communications with the RC receiver. You get your IMU pulling done so that you can stabilize the flight controller. Uh, I added a couple of PID loops. I probably need to clean up a lot of the stuff that I've been prototyping, and there's going to be probably a stream that's going to be focused on this. The altimeter I haven't played around with. That's kind of a late addition. The communications with the single board computer I haven't done too much about. It's going to be a UART based communication loop, and there's not much to it other than every, let's say, 1 millisecond you go ahead and pull your UART buffer, see if there's anything there, read it out, put it in another buffer, and then you try to interpret what has been sent to you. For the most part, I haven't yet decided what my command structure is going to look like. There's going to be a command byte that's going to be sent by, let's say, the single board computer to the flight controller. And let's say the flight controller looks at the byte, it sees, oh, it has a ping kind of command, so the flight controller might respond with acknowledge, so that the single board computer knows that the flight controller is alive and well. It hasn't crashed or anything like that. Crashed as in the code hasn't crashed, not that the system hasn't crashed. then the single board computer might send another byte command or command byte, and that command might say something along the lines of, get IMU data. And then the flight controller will respond with the IMU data. Or the flight controller might send a command like set bearing that or set heading to that. So it's going to, the flight controller will set the set points for the PID loops based on what comes across from the single board computer. Over here, I have been playing around with the web hosting stuff and the computer vision, and that's actually going to be coming up next on the list of stuff to talk about. I haven't played around with the guidance yet. I haven't really looked into, the UART on the single board computer, other than, I shorted the RX and TX pins on the single board computer and made sure that the loopback on the UART worked. Initially, I wanted to use a Raspberry Pi Zero as my single board computer just because of its super low power usage and its uh, very small footprint. However, it is a very low power computational power device, so you need to have something to accelerate its computer vision or machine learning ability. And there is an AI accelerator by Google called Coral. Unfortunately, they're all sold out of it, so using that as a means of object tracking has been put on hold for now until I get one of those accelerators in, and then I might try to use uh, a Raspberry Pi Zero again. If that still proves to be way too low power, computational power once again of a device, then I might switch to a higher powered Raspberry Pi. In the meantime, I'm using the Upboard core or the Up Core board by Aeon. It's an I no, it's not an i3. It's a Celeron, I think, or maybe a Xeon. Let me find it up. Core board. It's nice and powerful. Unfortunately, it's also much more expensive compared to so it's much more expensive than a Raspberry Pi. Maybe the Upcore with 1 gig and 16 gigs of eMMC or storage, it's somewhat comparable to the higher end Raspberry Pi with lots of RAM and but other than the super low end Upcore, uh, they are way pricier, which is why I wanted to use the Raspberry Pi Zero with the accelerator, because the Raspberry Pi Zero is like $20. The accelerator is, I think, about $60. So you have $80 for your computer vision node, and then plus the camera. Here, on the other hand, these range from 120 to 190 bucks, and this does not include, this ships from Europe, so this does not include any customs taxes. If you were to buy this from, let's say, Mauser, this will cost you, I think, an extra 20 or so dollars on top of whatever you see here. So let me go to mauser.com. Let me bring this over. So let's see, what do we want here? We want up core. Let's see if we can find that. And we're looking not for that. Oof. SPC. Single board computers. Set single board computers. We want single board computers by Aeon. And of course we don't see anything here. So let me just start from scratch. Aeon. We want the smallest footprint available. I can't really see what it is there. Series, do they have a series here? Let me apply the filter first. Let's see. We want installed RAM. I think they might have actually gone out of stock on the board that I got. Let's see. Single board up core. I'm looking for, so this might be it, 4 gigs and 64. Is that it? 4 and 64. All right, so on the Aeon website, it's 190 bucks. Once it's imported, becomes 210. So, you know, in reality, if you're buying this from the US, it's going to be more than 190 bucks. But this is the one I'm using, the up-core with 4 gigs of RAM and 64 gig eMMC drive. So I wanted to, you know, we're coming up on half an hour now, and I wanted to close out with a little demo. So let me remote into my single board computer. So here we are. That was me playing around with the serial on there, and I got the loopback working. So let me clear, and let's see, ls. Okay, I should be able to cd into the repo here, and then ls. Okay, I think I have a quick demo, or it's not really a demo, but it's a prototype, which makes for a nice demo. So let me navigate in there. Okay, so I think this should work. So let me start up this app. Python 3. Oops. It's really Python 3. Okay. I had a command in here somewhere. Gotta activate my OpenCV in Flask environment. Let me start this up again. And camera ready. So we should now be able to navigate to the website that's being hosted, and there I am. Let me grab something that I can track. So I got a little box. This is the box that the camera for the upboard came in. So what I can do is, well, I think I'll just use my hand. Here's my hand. I can draw a box around it. I can set the tracker, and there it is. This is kind of a busy environment here. You know, I have my microphone right here. Uh, this uh, 2x4 here. There's a camera right here for overhead views if I'm doing stuff on my desk and I want to film it. Got, you know, two screens, my work laptop off to the side. Got a big mess here, but you know, it's still managing to track my hand reasonably well. Like you saw, oops, now it's stuck on the, got confused what's my hand and what's the microphone, but you know, it's tracking reasonably well. If you have a less busy uh, environment, I think this tracking will work well. One thing I want to try uh, is to use the GoTurn tracker in OpenCV. That's a tracker that uses uh, machine learning. It has a trained neural network, and the trained neural network, it basically, what it's been trained on is how to track objects once you've shown it what an object, or it has a general idea of what it needs to do to track an object from frame to frame, and you just give it some object and then it will use that generalized knowledge to track the object that you gave it. So I think that's going to be it for now. We're right at half an hour for now. So that's it. Thanks for watching and have a nice